Hello, so now we've done calculations with a velocity graph, or excuse me, with a position graph. We've looked at velocity graphs and making velocity graphs. Let's take a look at how you can calculate various things from the velocity graph. Now, from the last video, we know that displacement is our change in position, okay, your final position minus your initial position, and your instantaneous velocity is just your velocity at a given point. So your velocity at a given point in time on a velocity graph is just the value at that time. Okay, so wherever that line is, at that time, that is the velocity. Okay. And the new one we're going to look at here, so wherever it is, acceleration. So our acceleration is defined as our change in velocity per change in time. Okay, and if we look at a velocity graph, our change in velocity over our change in time is our slope. And so we're going to look at how to calculate these three things from different velocity graphs. The first one I'm going to talk about is just the instantaneous velocity because that's the easiest to see on a velocity versus time graph. Here we can see if we look at time 0, we're at 4 meters per second. If we look at time 1, we're at 4 meters per second. Okay. If we're at time 2.5 here, we're at negative 2 meters per second. 3, we're at negative 2 meters per second. Okay. This doesn't change because they're horizontal lines, which means it's constant velocity. And so if we want to know our velocity at any given time, you just look at the dot where it's at. Okay. We're going to look at our situation. 2 soccer players were kicking a ball back and forth. The first player kicked the ball and it traveled at a constant 4 meters per second for 2 seconds. It was then kicked back and moved at a constant 2 meters per second for 2 seconds. Okay. When the first player, well, let's change colors here so we can keep track. Back, constant 2 meters per second for 2 seconds. When the first player ran up to it and stopped it. Okay. So it's already graphed for us. Try to save some time on this video here. 4 meters per second for 2 seconds. It's a horizontal line because it's constant. Okay. It then is kicked back. Okay. It changes velocity very quickly. Okay. You cannot make this a straight line because you can only be traveling at one velocity per any given time. And so it's going to be slightly angled, but very steep. Because if you've ever seen a ball get kicked, it does not take long for it to be going forward and then backward. Okay. And then it moves at a constant 2 meters per second for 2 seconds after that. So from 2 to 4, we're at negative 2 and stopped it, which means we are at 0 meters per second. Okay? And we can see it getting stopped there on the graph. Now the acceleration, okay, we're going to look at acceleration at, say, time 1. It's a horizontal line, so our acceleration is just 0 meters per second. Okay, it's not changing, it's not accelerating. Okay, time 3, same thing, 0 meters per second. Okay, it does quickly accelerate at time 2 and time 4, but at the given time, I don't want to look into because I'd have to give you a time over which that took, and I don't want to get into those fine details. We'll look at acceleration more so on the next question. Okay, so now we're going to look at displacement. There are 2 things we can do. We can use the same displacement equation from earlier because we're at constant velocity, and from our last video, we know that position is equal to velocity times time if it's constant velocity plus our initial position. But the interesting thing about this, though, is if we look at our graph here and we want to use our 4 meters per second for 2 seconds here at the beginning. Okay, so we're going to do x equals 4 meters per second times 2 seconds plus 0 meters because that's our initial position. Note, it's not 4 meters because this is meters per second. Okay, make sure whenever you're doing a graph, think about what graph you're doing. You start moving at 4 meters per second. We get to make up our own initial position, so we're going to call it 0. Okay, 4 meters per second by 2 seconds. Now let's take a look here on this graph. This shows up here. This line is 2 seconds long, and here, starting at the x-axis to here, is 4 meters per second. So we're going to multiply them down here, and we're going to cancel seconds out, and it's going to be equal to 8 meters. Interesting. If we multiply this length versus this height here, we end up getting this area, and that area is also equal to 8 meters. So what that means is my displacement on my velocity graph is equal to the area between the velocity line and the x-axis, okay? Believe it or not, this gets into some calculus stuff, but we're going to keep it simple, okay? You all know the area of a rectangle equation is just length times height, okay? We're going to see triangles here in a minute, but again, we're going to keep it simple with those. And x-axis, okay? So let's use that here for the next one. Our velocity here, we have negative 2 meters per second. And our time here is 2 seconds. So our area in there is going to be equal to negative 4 meters. Okay. Note that negative here is important. Don't forget your negative because you're going to mess it up. Okay. And then here at the end, we have 0 displacement because we're not moving. 0 velocity means we're not moving. And so displacement equals 0 meters. Now to figure out my overall displacement, we can stay here at, give me some more room, okay, at time 2 seconds, we are located at 8 meters. Position equals 8 meters, okay, we found that right here, we found that over here with our area of that. So at time 2, we've moved forward 8 meters. So then from time 2 to time 4, we found out that we've moved back 4 meters. So at time equals 4 seconds, we're starting at 8 meters at 2 seconds. We're going to go backwards 4 meters. We're going to end up being at 4 meters. So our final position is 4 meters. Our initial position, because after that, I guess we could do the last second, which is 0 meters displacement, so it stays there. So our x final is 4 meters. Our initial was 0 meters, which means my displacement was 4 meters minus 0 meters for a total displacement of 4 meters. Okay, here in the next video, I'm going to look at how to relate these two graphs with a position, or this graph with a position graph. For right now, we're going to stick to just these calculations. We're going to look here at one more example real quick. I didn't give you the words on this one. It's just we started moving at negative 2 meters per second is my initial velocity. I accelerated at some rates until I was moving at 4 meters per second at 3 seconds. Okay, so my acceleration we said is equal to my change in velocity over my change in time, or my slope here. So to find my slope, my final velocity is 4 meters per second. My initial velocity was negative 2 meters per second. Okay, keep track of those negatives. My final time here is 3 seconds. My initial time, seconds, was 0 seconds. Okay, so that gives me 6 over 3 meters per second over seconds, gives me an acceleration of 2 meters per second, which means every second we were traveling, the velocity increases 2 meters per second every second. It's constant acceleration because my slope here is constant, so it's not changing. Acceleration is not changing. My velocity, however, is increasing because my acceleration is 2. Displacement, again, we are going to look at that area between my line and the x-axis. Okay, so we draw some lines here. We've got first triangle and the second triangle. We separate these two out because here at 1 second, that's not very nice. Okay, oh no. There we go. Here at 1 second, we've stopped, okay? We've stopped because our initial velocity is negative, so here we are moving backwards. At time 1, we stop. Then here we're moving forwards. The first thing you want to do is find out how far do we move backwards, okay? The area of a triangle is equal to 1/2 base times height. So here we've got 1/2, my base is negative 2 meters per second. Or excuse me, my height, kind of flip those. Height is that, base is 1 second. So we move backwards negative 1 meters. The second one we've got here is 1/2 4 meters per second and 2 seconds, which gives us 4 meters forward. to find our overall displacement, we just add those two. So displacement equals -1 plus 4